Alright, so today we're going to start section 1.3. We won't finish it. We'll finish it next class period. But this section is reasoning and logic. And the first section of looking at this is going to be talking about sort of some language. Just a moment. There we go. Alright, so the first thing I want to talk about is what a statement is. Again, you've seen this description if you have taken music grade math, and if you haven't, you kind of know what a statement is just from the things you've encountered so far. So a statement is basically a sentence that's either true or false. So for example, I ate cereal for breakfast. That would be a statement. What did I eat for breakfast is not a statement, it's a question. Okay. Another non-statement would be something, a common one is a command. For instance, if I say, go eat your cereal. It's not a statement, it's not a true or false, it was a command, I told you to do something. So those are the two common sort of non-statements or questions and commands. A negation for a statement has some notation. So if we have a statement that we have notated with a small letter P, then the negation notation has a tilde in front of it. It's the same tilde that's on your computer screen. Okay, it kind of looks like the approximately ones, except that those are usually double stacked. So you've got a tilde, and the notation means not P, as in the opposite of. So if I had the statement, I ate cereal for breakfast, the opposite of that is not, I ate eggs for breakfast. Right? I mean, that would mean I maybe didn't eat cereal, but that's not the opposite. I could eat anything else, and it'd be the opposite. So we simply would use the word not involved there. So I did not eat cereal for breakfast. That's a pretty straightforward example, and they aren't always that straightforward. The cases that are not that straightforward are the ones where we have quantifiers involved in them. So there's two different types of quantifiers. There's universal quantifiers, and there's existential quantifiers. Okay, so you're going to sound really smart when you go over to the GC later and you start talking about the words universal and existential, right? Yes, you are, of course. All right, so here's the deal. Universal means it's something that applies to everything. Existential means it's something that applies to one item or a small collection of items. Okay, so universal quantifiers use the words all, every, no, none. Those are the phrases that you see. So you see things like all people are sinners. You see things like no one sunbathes in the rain. No, something like that. Okay. So statements where they apply to everybody, or to no, or the word no and they apply to everybody. Okay. Those are the kind of things that are universal quantifiers. Existential quantifiers refer to one or a few. And so we see words something like there exists, or we see some word that's like the word some. For example, some cats go to heaven. Maybe they do, maybe they don't. That's not the point. Okay, this isn't the true-false issue. It's the language issue that we're talking about here. The word some. It doesn't mean they all do. It doesn't mean none of them do. It just means some of them do. I could just as well put the statement in there instead of the word some. I put the word there exists. There exists a cat that goes to heaven. Okay? So why does it matter? It matters because the previous slide, when I changed the original statement from I ate cereal into the negation I did not eat cereal, it becomes much more complicated when you do negations when you have quantifiers. Alright? So we're going to take a look at doing negations for a couple of these that have quantifiers involved. So here's the basic idea. If you have a universal quantifier, that word all, no, none, it turns into an existential quantifier. And if you have an existential quantifier, the word some or there exists, it turns into a universal quantifier. So they're sort of like negations of one another, those two statements, okay, those two phrases. So do I have an existential or a universal quantifier in example A? Universal, and it is the word all. So I have to take the word all and turn it into an existential quantifier. Okay? We can use the word some, or we can use the phrase there exists. Haley said some, so that's the one we're going to do. So we're going to change all into some. And then after that, the rest of the phrase becomes the opposite of what it was before. Some what? Some dogs don't or do not, whatever, go to heaven. You see, the negation of all dogs go to heaven, all we really have to do is find one that doesn't, and it makes the statement false. Right? So very quickly we turned into a class that was all female, and all it took to make us not all female was Brendan. One, right? One in the class is not female, so no longer can I say everyone in the class is, because there exists one who's not. Make sense? I don't need no one in the class to be female. I just need one person not to be. I don't need no dogs to go to heaven. I just need one not to. Okay. Now we're going to go the other direction. This one right here has what kind of quantifier? Well, and let me do it this way. I'll just put the sum. Okay, existentials, the word sum at the beginning. Okay? So you have two choices. The word sum can be changed into what? All or none. And depending on which one you do will depend on how the rest of the statement follows. And either one is perfectly okay. All right, so somebody pick which one you want to do, and I'll do both of them, but which one you want to do first? All. Okay. All. All right, I need the opposite of some of my classes are hard. All of my classes are not hard, so be careful, right? Because you've got hard and you've got easy, and I guarantee you've probably got some classes somewhere in between, right? So you want to be careful about sort of changing the words around too much. So we can say all of my classes are not hard. Okay, so that's one way I could rephrase it. But I could have chosen, instead of the word all, I could have chosen the word none. And if I chose the word none, that would be okay as long as what follows makes sense with it. So again, some of my classes are hard. What's the opposite of that? None of my classes are hard. So notice, by changing it that way, the rest of the phrasing actually didn't change at all. But both of those pieces that I wrote down in green have the exact same meaning, don't they? They're just phrased differently. And that's okay. So half of you are going to do one, and a third of you are going to do the other one, and the rest of people are going to get it wrong. Okay? No, you're all going to do it right. But you have choices, I guess, is my point, right? The point is that there's more than one way to write it that are equally good. Okay? All good? Okay. So, do you remember these guys from contemporary math? Those of you who've taken truth tables? Okay, so we're not going to get quite as involved in truth tables in this chapter as we did in contemporary math. Some of you are thinking, fabulous. Others of you are going, what's a truth table? All right, so truth tables are used to show all possible true or false patterns for statements. So I want to show you a truth table for a few examples. The first one is for a negation. So a truth table takes a statement, P, and it does, in this case, another statement, which is the negation, tilde P. There are only two things for a statement that are possible. The statement is either true or it is false. And this is what we do when we tell small children, and sometimes we tell ourselves. You either told the truth or you lied. We can talk about something being a white lie, but it's a lie, right? Because the statement you either made was either true or it was false. And that's what's going on here. So if the statement is true, then what do you suppose the negation is? False. And if the original statement were false, then the negation would be true. Okay. But we can also join statements together. And when we join statements together, that's called a compound statement. All right, so I ate cereal for breakfast and I drove to school. They may or may not have a relationship to one another. Those two wouldn't necessarily, but they could. I ate cereal for breakfast and I drank milk for breakfast. They both had to do with breakfast in that case. Okay? So a compound statement can join words in 3 different ways. They can use the word and, 2 things both happened, right, and. They can use the word or, one or the other or both happened. Or they can use the phrase if then. If this thing happened, then this thing happened. Those are our 3 basic connectives for compound statements. All right, so I want to talk about the 2 that were listed first, the and the or. All right, so the first one is called a conjunction. A conjunction is an equivalent of an and statement. And it's true if and only if both statements are true. So if I say, I ate cereal for breakfast and I drove to school, you know that the only way that that's true is if the first statement's true and the second statement's true. Because I used the word and that's what we mean when we use English in that way. We mean they're both true or the whole statement wouldn't be true as well. So I want to show you how we do a truth table with these guys. So our 2 statements are going to be the letters P and Q. And when I create a truth table, I create a column for P and a column for Q. Okay. A conjunction has the symbol V. That's the and symbol. Okay, so think about it like this. Most of you have smartphones, and even those of you who don't have phones that text. Most of you do. And many of you use language when you text that is not the language that you use when you talk to me, right? Or when you send me an email, it's different language, it's texting language. And if you send me a text, I probably wouldn't know what you're talking about because I don't know much of it. That's what we're doing here, all right? We're using mathematical language to simplify the expressions, shorthand, okay? That's what we're doing. So the symbol that joins P and Q together with this V between them is an and symbol. This means P and Q. I totally told you the wrong one. It's an upside down V. Sorry. It's this one. I'm already on my disjunction. It's an upside down V. Because it looks like, what did somebody say? It kind of looks like an A for and, or an N for N, depending on what you're using. Yeah. When we do sets, sometimes you see it used as an upside down U for set, and it means its corresponding step. So I'm sorry, we'll get the right one in there. Okay, so one possibility with my 2 statements is that both of the statements were true. Okay, so I ate cereal for breakfast and I drove to school. One possibility is that I did in fact eat cereal for breakfast and I did in fact drive to school. Both statements were true. Another possibility is that I ate cereal for breakfast, but I rode my bike to school, or I walked to school, or something, or I just didn't go to school at all, right? So the second statement was false. I did not drive to school. The third possibility is that I did not eat cereal for breakfast, but I did drive to school. And what's the one I haven't listed? False and false. I didn't do either of those things. Maybe it's Saturday and I slept in. Okay, false and false. Now, this pattern is always the same. When you have 2 statements, the pattern is always TT, FF, and then they oscillate TF, TF. Pattern always. Okay? TT, FF, TF, TF. And this is a conjunction, which we said just a moment ago means that the only way that the and statement is true is when what happens? They are both true. So that first line on the top, where they are both true, if they are both true, then the and statement that joins them is a true statement. Otherwise, it's false. So all other lines of this are false statements. That's what happens when you have a conjunction and statement. A disjunction is an or statement, and we'll get our symbol right from the get-go this time. That's B. An or statement means one statement or the other, or both, are true. So if I make the statement, I ate cereal this morning, or I drove to school, all it takes for that statement to be true is one of those pieces being true. And if they're both true, then it's still true. Right? We're using the type of or that is what's called an inclusive or. It means that if both statements are true, the statement is still true. So we're going to create the same kind of a truth table as before, P, Q, but we're going to create the column that's P or Q. So we mentioned just a minute ago the pattern's always the same. So I've got T, T, F, F, and then T, F, T, F. And the pattern just always is the same because it covers all the possibilities. I want to make sure I represent every possibility for my two statements. So if both statements are true, is an or statement true? Yes. If the first statement is true and the second statement is false, is the or statement true? Yes. If the first statement is false and the second statement is true, is the or statement true? Yes. If they're both false, is the statement true? No. It is not. So the only time that the statement will be false for an or statement is if both pieces are false. All right. I'm trying to think if I did. I don't think it comes up in your homework. If it does, we'll talk about it when it comes up. The if-then statement, which we do in contemporary math, I don't think it comes up in the homework, which is why it's not in the lesson. In the notes, if it does, we'll pause when you guys are doing group work next time, and we'll account for that then. Okay. All right, we're going to create a truth table that combines a couple of elements that we've discussed. It combines which one? Is this a conjunction or a disjunction? Conjunction, because it's got the upside down V. What else is here that wasn't here before? The not. It's got a negation involved, right? So, when we start our truth table, we start with a column for P and a column for Q. And that's great, but I don't want to combine P and Q. I want to combine P and not Q. So I need a column for not Q as well. Notice that doesn't give you the right to eliminate Q from having its own column. Q has a column. We just have an additional column for tilde Q. And then we have a column that represents joining them together because we have the two pieces listed in their own columns that we want to join. We want to join the statement P with the statement tilde Q, and we want to join it with an and statement, which is a conjunction. So I need columns representing all of those pieces. P and Q, though, you know what those columns look like. So even if you can do no further on the problem, you can fill in column P and Q, right? They're always the same. So what is column P going to say? True, true, false, false. And what is column Q going to say? True, false, true, false. Tilde Q takes column Q and does what? It does the opposite. So what will tilde Q look like? False, true, false, true. And then the column of our actual interest, what we really wanted to find, is P, which takes this P column, and tilde Q, which takes this column, and it compares them with the statement and. When is an and statement true? When they are both true. So if I have the first one true and the second one false, the and statement is false. If I have the first one true and the second one true, the and statement is true. If they have the first one false and the second one false, the and statement is false. And if I have the first one false and the second one true, then the and statement is false. And that's the truth table that we wanted to create. All right. Example 3 looks a little bit different. So looking at the language, I don't mean looking at these symbols, but looking at the language, what's different about what you're asked to do between examples 2 and example 3? It's a conjunction, but you're looking at the symbols. Before we get to the symbols. Truth value. It has the word value instead of the word table. Do you guys see that? Okay. That's important. So if you're creating a truth table, you have to create the whole table. If you're asked a truth value question, it means that they actually have told you what P and Q are. That is, they've told you whether they're true or false. And that's kind of cool. Because what that means you have to do is you have to create only one line of the truth table instead of the whole truth table, which is obviously less work. So don't overlook an opportunity to do less work. As a general rule of thumb, that's not a good thing to say, but right? I mean, like, really, you want to look at what they're asked to do. Don't do more work than the problem's asking you for. This problem does not ask you to do a truth table. But it does ask you to figure something out based on a truth table, but just one line of it. So we're going to create the column headers much like we did before, but our table portion is going to look much condensed. So we're still going to have a P and a Q. But what else do I need? Not P and not Q. And then it was already mentioned before, how are we joining them? With a disjunction, right? This time instead of a conjunction. We've got the V between the or statement. Okay, so we've got this sort of set up the same way as before. It's just that we were actually told that P is false and Q is true. So I don't need to explore any other possibilities. No other possibilities are happening. P's false, Q's true, end of story. If P's false, what is tilde P? True. And if Q is true, what is tilde P? False. And then the last statement wants me to join these two statements together with the disjunction or. So if I have a false statement and a true statement, is the disjunction, the or statement, false or true? True. True. And then I have to answer the question, because the question said, what is the truth value? And the answer is that it is true, because it's the last statement. So the answer to the question is that it is a true truth value. So in other words, when P is true and Q is false, then tilde P or tilde Q is a true statement. Okay? We're going to join this with some language here in a moment. So sort of right now it just looks like a bunch of letters and symbols and great, but why, right? I promise we're getting to the language. I want to talk about what it means to be logically equivalent and De Morgan's laws. So two statements that have the same truth value in every possible situation are written as P and Q, and what's between them? What does it look like? Like a barcode that it kind of has. Can anybody see it any better? There's actually three equal signs. It's like an equal sign, but there's 3 bars instead of just 2, right? So those 3 bars actually mean that they are logically equivalent. Okay? So it's kind of like having an equal symbol, but we're talking about it in terms of a logic argument, so the symbol looks just a little different. It's got 3 bars. De Morgan's laws have that possibility or that pattern. So I want you to see this because it's pretty interesting. This tilde right here is outside of a set of parentheses, right? This is kind of like in algebra when you have a negative on the side of a set of parentheses. And one of the operations that you have in algebra is this idea of distributing. Okay? So when you distribute a negative, you have to distribute it to each piece. Alright? So you see this tilde affects P becomes tilde P. The tilde affects Q, it becomes tilde Q. But what else also happens? The sign switched. Right? Yeah. So our conjunctions become disjunctions. And likewise down here, our disjunction becomes a conjunction. So it's like it's distributing, but it's distributing to all 3 pieces, each of our individual statements, and the symbol that joins them. That's De Morgan's laws. So we're going to do De Morgan's laws for just a plain problem with symbols here. So if I went to Morgan's laws to write the negation of P and tilde Q, what would I have? How would it start? Tilde P. Okay, so Beth gave me one answer. Someone else. What's going to be next? Disjunction. And then just plain Q. That's exactly right. So these are equivalent. And the reason that's helpful back into language has to do with the language we use. We're going to get on example 6. Where do you got? I have example 5 where I want to show you something. Okay? What we're going to do on example 5 is we're going to verify, in essence, with the truth table, that the answers really are logically equivalent. So let me show you what that means. We had, on the example before, tilde P and tilde Q like this, right? And we created the statement that said tilde P or Q like that. Those were my two statements that we said were logically equivalent, correct? Okay. So we're going to verify that this really worked, and we're going to do this with a truth table. So just like in algebra, we work inside of a parenthesis out when we have parentheses. So I start with P, and I have Q, but inside the parenthesis, what else do I have? But tilde Q first, right? Then what? P and tilde Q, all of it, right? And then once I've established whatever's inside there and I've figured that out, then I can move outside the parentheses to tilde. So I've got tilde P and tilde Q, like this. So this is one of my two truth tables. What does column P say? True, true, false, false. What does column Q say? Good. All right, what's tilde Q going to say? False, true, false, true. And then it asks me to consider P and tilde Q with what symbol? And. So if I have a true and a false, is that and statement going to be true or false? False. That is false. How about true, true? False, false? False, true? Excellent. And then what happens when we negate something? They all switch. So I want to take my last column. I want to look at the previous column that I just created, and all the T's turn into false, and all the falses turn into true. So I'm going to take false and turn it into true. True becomes false. False becomes true. False becomes true. And that is the truth table that created that last column. But I want to compare that to doing it with the De Morgan's law operation having happened already. So the first two columns look the same. They've got P and Q. What's the next column going to look like? Tilde P. And then I only need one more column, right? So hey, that was handy. Last column is tilde P or Q. Less work. Agreed? All right, what's column P going to say? True, true, false, false. How about column Q? How about tilde P? False, false, true, true. We're almost done. We're supposed to consider tilde P and Q with the or statement. True or false is true. False or false is false. True or true is true. And false or true is true. And if you look at the last column in both of these, what do you notice? They're exactly the same. And if you created the problems and we did the truth tables properly, they should be the same because they're supposed to be logically equivalent. All right? I will see you all on Friday. Have a wonderful couple days.